Iron is an incredibly abundant substance, and not only that, and when we refine it into pure iron, we can get really useful materials. We can shape it, we can mold it, we can have a pretty strong, relatively cost-effective material to work with. The only problem is that iron corrodes incredibly easily when exposed to oxygen. And so one of the methods that we actually use to protect it is a method that we call cathodic protection. And this is essentially adding on a more reactive metal to the iron so that the iron itself doesn't lose electrons. What we want to look at is basically kind of the structure of how we would have something set up. So what we would have is our sheet of iron, and on the surface of that iron, we actually coat it with something that is more reactive. In this case, we're using zinc. So what do I mean by more reactive? Well, I mean more reactive with oxygen. In other words, we need a metal that is more likely to be oxidized than iron is. And we can find this by looking at a list of standard reduction potentials. You see, iron has a standard reduction potential of negative 0.44. If we found something that is more likely to be oxidized, in other words, it has a more negative or a lower standard reduction potential, something like zinc, we can actually get that zinc to give away its electrons instead of the iron having to give away its electrons. I should mention you can actually use any of the substances that are more likely to be able to oxidize than iron, but zinc is a pretty good choice because you are actually able to coat iron quite easily with zinc. So what's going to happen over the course of this reaction is, first of all, our oxidation is going to take place. So in order to have oxidation, you need to have reduction. And what's going to happen is that oxygen is actually undergoing the same reaction that we saw in the previous video. So oxygen is reacting with water, and it's going to gain electrons, and in doing so, it's going to create hydroxide ions. So that means we do need water around, and in the water, there is actually going to be oxygen that dissolves. That oxygen is then going to combine with the water, and they are going to react. Now, you may think that they are going to react with the surface of the zinc, and they can, but you can actually even leave the iron totally exposed and have this reaction still work, as long as the iron is connected to the zinc. You see, what's going to happen here, for this reaction to work, you needed the oxygen and the water reacting with the surface of a metal, and in doing so, they are going to gain 4 electrons. Those 4 electrons are going to create our hydroxide. But those electrons can actually be given away from the zinc to the iron. Because zinc is more likely to be oxidized than iron, it means that iron can actually oxidize zinc. So as the zinc is losing its electrons, the zinc is also entering the solution as Zn2+. So solid zinc is actually giving away its electrons. In order to balance our equation, we actually need it to give away 4 electrons. And what is it actually giving those electrons to? Well, it's giving them to the iron. You see, as the iron loses these 4 electrons, so as our iron is actually losing those 4 electrons and becoming Fe2+, oh, and we should balance this, so we need 2's in front, then the zinc is actually going to supply the Fe2+ with electrons right away, making sure that the iron never actually oxidizes. This type of protection is called cathodic protection. By having oxygen actually react with the surface of that metal, coating it with a more reactive metal will allow the more reactive metal to supply electrons. By supplying electrons, you actually avoid the oxidation of the actual metal, such as iron, that you're trying to protect. In this case, the zinc has a special name. We call the zinc in this reaction a sacrificial anode. Because the zinc is being oxidized, it is the anode, but we are actually going to lose it over time in order to protect the iron. Essentially, the zinc is sacrificing itself in order to protect the iron from corrosion. This is a really, really important way of protecting metals. It's something that we do to protect iron ships as they float across a very salty ocean to protect them from corrosion. It's a way that we can actually make sure that things like your hot water heater aren't losing all of the actual iron on the inside to the oxygen and water that are inside of the tank. We can use different metals to create different sacrificial anodes, and a really common one is actually magnesium. Magnesium is actually supplied in a lot of different reactions as the sacrificial anode because it is much more reactive than iron. It is also quite abundant and fairly cheap to actually use, and so it makes a really good sacrificial anode. Protecting metals from corrosion is really important, and this is one method. You can also use things like paint and just protect the oxygen from getting to it, but using a sacrificial anode or cathodic protection actually supplies you a much more long-term solution. Eventually the sacrificial anode will run out, but you can reapply it quite easily by using electroplating or maybe just dipping that metal into a melted bucket of zinc until you can coat the surface of it once again. This is just one method that we can use to protect from corrosion, and hopefully it helps you get an understanding of ways that we actually use materials to protect things that we've created.